Learn C pointers in 20 minutes. Introduction to pointers. I'm Behnam Jafari and welcome to Picobit Tech. In this video, we're gonna unlock one of the most powerful concepts in the C programming language, pointers. Pointers tell us where data lives in memory. Instead of working only with values, pointers allow us to work with memory addresses directly. This gives us control, flexibility, and performance that higher level language simply cannot offer. Understanding pointers is essential for low level programming, embedded systems, memory optimization, and advanced data structures. So let's begin our journey into the world of pointers. What is pointer in C? Why do we use pointers? Imagine you have a house in New York where the house itself represents the data and the address of the house represents the memory address. A pointer does not store the data itself, but only stores where that data is located in memory. Now let's see this idea in the C language using a real memory example. We define three integer variables. Int a equal 50, 25, 35, 45. Int b equal 33, 34, 35, and 36. And int c 61, 62, 63, 64. And since each integer occupies 32 bits or 4 bytes in memory, we then define three pointers. Int p1 equal address of A, int p2 equal address of B, and int p3 equal address of C, where each pointer stores the starting address of its corresponding variable. If we visualize the memory layout, we can imagine three boxes stacked vertically. The memory layout, we can imagine three boxes stacked vertically, each corresponding 32 bits of data. The first box belongs to P1, starting as address of 5FFE98 and ending at address of 5FFE9B, and it contains the value P1 equal 15, 25, 35, 45. The second box just below it belongs to P2, starting at 5FFE9C and ending at 5FFE9F, containing P2 equal 33, 34, 35, and 36. And the third box belongs to P3, starting at address 5FFEA0 and ending at 5FFEA3, containing P3 equals 61, 62, 63, 64. An important detail here is that this system uses Little Endian memory format, which means the least significant byte of a number is stored at the lowest memory address. So inside each box, an byte with the smaller value appears on the left side, representing the lower address, while the most significant bytes appear on the right at the higher address. Therefore, even though we write a number like 15, 25, 35, 45 in this order, in the memory, its bytes are arranged from left to right, starting with the least significant byte, 45. This is very important. This is why understanding Indian is critical when working with pointers and memory in C. Because you are not just reading values, you are reading how those values are stored byte by byte. And this is how pointers memory layout. A Little Indian architecture, this is this is how pointers memory layout and Little Indian architectures work together in C language. But why do we use pointers? We use pointers because they allow direct access to memory, letting us working with the location of data instead of just its value. Pointers make program more efficient by avoiding unnecessary data copying. Allow functions to modify regional variables and form the foundation of arrays, strings, and dynamic memory allocation in C. Most importantly, they give a low-level control over memory, which is what makes C powerful for system-level and performance-critical programming. Pointer declaration and initialization. A pointer is simply a variable that stores the address of another variable. To declare a pointer, we use an asterisk. For example, int asterisk p. Here p is the pointer and asterisk p represents the value stored at the address held by p. In C, pointers can be defined in two professional and commonly used ways. The first approach is to declare the pointer and initialize it with null, and then assign a valid address to it later in the program. This is considered a safer practice between it clearly indicates that the pointer is not yet pointing to any valid memory and helps prevent accidental access to an uninitialized pointer. The second approach is to initialize the pointer at the moment of declaration by immediately assigning it the address of an existing variable. This method is cleaner. This method is cleaner and more concise, and it is typically used when the target address is already known at the time the pointer is defined. Both approaches are correct and widely used, and choosing between them depends on code structure, safety requirements, and when the pointer's destination becomes available. Understanding data types and pointer types. Every pointer in C must have a specific type because the type determines how many bytes of memory should be read when dereferencing. If a memory location contains a byte that represents an ASCII character, reading it with a char gives us a character, but reading the same address with an int interprets the same bytes as an integer. This is why pointer types matter. A mismatch can lead to incorrect data, corrupted memory, or unexpected behavior. See the example, please. In this example, we define an array of 4 bytes initialized as 41, 0, 0, 0. where the hexadecimal value for 1 represents the ASCII character A, and the remaining bytes are 0. By casting both of them to point to the same memory location occupied by the byte array, although both pointers reference the same address, they interpret the data differently. When we dereference the char pointer and print it using C, only one byte is read from memory and the character A is printed, while dereferencing the int pointer causes the program to read 4 bytes at once. On a Little Indian system, the least significant byte is stored at the lowest memory address, so the 4 bytes are interpreted as 0000041, which corresponds to the decimal value 65. This example demonstrates how pointer types determine how memory is interpreted and how indents affects the way multi-byte values are read in C. Null pointer. A null pointer is a pointer that points nowhere. It holds the value 0, meaning it does not reference any valid memory location. Null pointers are extremely important because they help prevent accidental memory access. Before using a pointer, always check if it is null. Dereferencing a null pointer leads to undefined behavior and program crashes. Please see the example. In this example, the pointer is first initialized to null, which represents a safe and noun state. Later, the pointer is assigned the address of a valid variable. Before using the pointer, the program checks whether it is not null, and only then write a value through it. If the pointer were null, the program would simply do nothing, avoiding undefined behavior. This simple check is a common and important practice in embedded systems to ensure safe and reliable pointer usage. Pointer arithmetic. Pointers support arithmetic operations, but only in the ways that make sense for memory management. When we increment a pointer, it moves to the next object of its type. For example, if we have an int or integer pointer, then p plus 1 doesn't move 1 byte forward. It moves by the size of an integer, typically 4 bytes. This is why pointer arithmetic is so powerful for navigating arrays. For example, using pointer arithmetic, we can access array elements without using indexing. For example, p plus I gives us the same result as array index I. Please see the example. Relationship between pointers and arrays. In C, the name of an array represents the address of its first element. That means array is essentially equal to address of array index 0. Because of this, pointers and arrays are deeply connected. We can assign a pointer to the start of an array, move through the array using pointer arithmetic, and read or modify elements through dereferencing. The same applies to a string, which are simply arrays of characters ending with a null terminator. Understanding this relationship makes working with array and strings far easier and far more efficient. See the example, please. In this example, we show how the name of an array in C works as the base address of the array, allowing pointers to access its elements. We create an integer array A with 3 values and a pointer P that points to the first element. Using A index 1, let's use access the second element directly, while P plus 1 pointer does the same using pointer arithmetic. Both give the same result, showing that arrays and pointers are closely connected and that pointers can be used just like arrays to navigate their elements. Another example, we demonstrate how the name of an array in C acts as the base address of the array, allowing both array indexing and pointer indexing to access the same elements. We declare an integer array A with 3 elements and a pointer P that points to the first element of the array. By using A index 1, we access the second element through the array name. And by using P index 1, we access the same element through the pointer. Both approaches return the same value, showing that in the C, a pointer can be used just like an array to navigate through its element efficiently. Pointers and functions, or return via arguments. When we pass a variable to a function, normally C uses something called call by value. This means a copy of variable is passed, but with pointers, we can give the function direct access to the original variable without copying variable. This is called returning via argument or caller pass pointer. This function receives a pointer. This function receives a pointer, and because that pointer holds the address of a real variable, the function can modify the original data. This technique is essential for returning multiple values from a function and for efficient memory usage. In this example, we demonstrate how to modify a variable's value using a pointer. We start by defining a function called set_to_0 that takes a pointer to an integer as its parameter and sets the value at that address to 0. In the main function, we declare an integer variable n with an initial value of 5. By passing the address of n to the set_to_0 function using the ampersand operator, we allow the function to directly modify the value stored in n. After the function call, printing n shows 0, illustrating how pointers can be used to change the original value of a variable from within a function. Pointers and functions, or return via argument. Another example, we demonstrate how a function can return multiple results using pointers as arguments. The compute function takes 2 integers, a and b, and 2 pointers, sum and diff. inside the function, we first check if each pointer is not null before storing the results, ensuring safety in case the caller does not want one of the results. If the sum pointer is valid, we store the sum of A and B. If the pointer is valid, we store their difference. In main, we declare two integers, S and D, pass their addresses to compute and then print the results. This technique allows a single function to efficiently provide multiple outputs to the caller. This is very important. Returning arrays and strings using pointers. In C, functions cannot return entire arrays directly. However, they can return pointers. This allows a function to provide access to arrays or strings by simply returning the starting address. We can return pointers to static arrays, pointers to dynamically allocated memory, pointers to string literals. Once the pointer is returned, we can use it inside the main function just like any other array. This is powerful technique for creating reusable, flexible, and efficient code. See the example, please. In this example, we define a function getArray that returns a pointer to a static array of integers. The array is filled with even numbers from 0 to 8. Since the array is declared as static, it remains valid even after the function ends, allowing the main function to safely access and print its elements. This approach avoids dynamic memory allocation while still demonstrating how a function can return an array via a pointer. Pointer to pointer or double pointer. We will go into more advanced details in the next videos. A pointer to a pointer written as int double asterisk P is a variable that stores the address of another pointer. This concept becomes very useful when dealing with dynamic memory allocation, multi-level data structures, and advanced function behavior. Double pointers allow us to modify not just a variable from a function, but the pointer that points to that variable. In this example, the program demonstrates how a function can allocate dynamic memory and update a pointer in the calling function using a double pointer. In main function, the pointer p is first initialized to null, meaning it does not point to any valid memory. The address of this pointer, address p, is then passed to the function allocate underline int, allowing the function to modify the original pointer itself. Inside allocate underline int function, memory is allocated for a single integer using malloc, and the returned address is stored in pp pointer, which directly updates p in main. The function then checks whether the allocation was successful, and if so, writes the value 99 into the allocated memory using double pointer pp. After returning to main, the pointer p now points to valid memory containing the value 99, which is printed to the output. Finally, the allocated memory is freed to prevent the memory leak, completing a safe and correct example of using double pointers in C. Function pointers. In C, even functions have memory address. That means we can store the address of a function inside a pointer and call the function through that pointer. Function pointers allow us to select functions and runtime, create callback systems, build lookup tables of a function, design flexible and modular programs. By storing multiple function pointers in an array, we can switch between different behaviors dynamically. Function pointers are widely used in operating systems, drivers, embedded systems, and real-time applications. In this example, the program demonstrates how functions pointers work in C. First, a simple function named add is defined, which takes two integers as input and returns their sum. Inside the main function, a function pointer named OP is declared with the same signatures as the add function, meaning it points to a function that takes two integers and returns an integer. The function pointer is then assigned the address of the add function, allowing OP to reference it. When OP with 2 and 3 arguments, which arguments by 2 and 3 is called, the function pointer invokes the add function indirectly, passing the values 2 and 3 as arguments. As a result, the function returns 5, which is printed to the output. This example shows how function pointers allow functions to be treated like data and called dynamically at runtime in C. Why do we need ampersand for variables but not for functions? In C programming, there is an important difference between variables and functions when it comes to address. For variables, the name refers to the value, not the address. So if we want an address of a variable, we must use the ampersand operator. But functions work differently. The name of a function already represents the address where the function's code begins. And that's why we can assign a function to a function pointer. No ampersand operator is needed because the function name itself is already an address. However, to access the return value of a function, just writing the function name is not enough. The name only gives the address. It does not execute the function. To run it and get the return value, we must write the function name followed by parentheses and include the correct argument. So remember, variable names refer to values. Use ampersand operator to get their addresses. Function names refer directly to addresses. No ampersand operator required. To get a return value, call the function using parentheses. Please see the example. In this example, the program explains how addresses work for both variables and functions in C. First, a simple function called twice is defined, which takes an integer and returns twice its value. Inside main, an integer variable x is declared and its address is stored in a pointer PTR. showing how the address of pointer ampersand operator is used with normal variables. Next, a function pointer fp is declared with the same signature as the twice function, and it's assigned directly using the function name without the ampersand operator, because the function name already represents its address. The program then prints the address of the twice function and the address stored in the function pointer, demonstrating that they are the same. Finally, the function is called in two different ways: directly using the function name and indirectly through the function pointer, and both calls return the expected results. This example clearly shows This example clearly shows how function names act as addresses and how function pointers can be used to call functions dynamically in C. Common pointer errors and how to avoid them. Incorrect pointer usage is one of the main sources of bugs in C programming. Common mistakes include using uninitialized pointers, dereferencing null pointers, accessing free memory pointer type mismatches. To avoid these errors, uh, always initialize pointers, check them before use, and make sure they point to valid data. Writing safe pointer code is one of the most important skills in C programmer must learn. Please see the example. Summary: pointers are one of the most essential and powerful features of the C language. They allow direct memory access, efficient communication between functions, dynamic memory management, and flexible program behavior. Remember to use null for initialization, match pointer types correctly, avoid dereferencing invalid pointers, check pointers before use, understand the relationship between pointers, arrays, and function. Our next video will be about structures and unions. To stay updated with our upcoming videos, please subscribe to our channel so it appears in your YouTube list for the future reference. Thank you for watching.